In a three-phase power system, a neutral wire is essential for carrying unbalanced currents. This means that the neutral handles any current that isn't equally distributed across the three phases. Now let's consider branch circuits. You have a setup with 6 circuits in total. 3 of these circuits are connected to phases A, B, and C respectively. The other 3 circuits are all connected to phase A. The question is whether you can use a single neutral wire for all 6 of these circuits. The answer is a definitive no. Here's why. When you have a balanced 3-phase system, the current flowing through each of the 3 phases is equal. Because of this balance, the neutral wire ideally carries little to no current. However, when the phases are unbalanced, which occurs when the current draw on each phase is different, the neutral wire steps in to carry the difference. In your situation, the 3 circuits connected to phases A, B, and C could potentially be balanced if each circuit draws a similar amount of current. If balanced, the neutral will carry minimal current from these circuits. However, the 3 circuits connected to phase A are inherently unbalanced. All the current from these circuits is flowing through a single phase, creating a significant imbalance. If you were to use a single neutral for all 6 circuits, this neutral wire would have to carry the entire unbalanced current from the 3 phase circuits, in addition to any slight imbalance from the A, B, C circuits. This can easily overload the neutral wire. An overloaded neutral wire can lead to several problems. Firstly, the wire can overheat. Overheating can damage the insulation surrounding the wire, increasing the risk of electrical shorts or ground faults. Secondly, an overloaded neutral can cause voltage fluctuations on the circuits it serves. This can negatively impact the performance of sensitive electronic equipment. Thirdly, in extreme cases, an overloaded neutral wire can melt or even cause a fire. To avoid these issues, the correct approach is to use a separate neutral wire for the 3 circuits connected to phase A. This ensures that the neutral wire for these circuits is sized appropriately to handle the unbalanced current without overloading. The circuits connected to phases A, B, and C can share a neutral if the load is expected to be balanced. However, even in this case, it's crucial to consider the potential for future imbalances and size the neutral wire accordingly. In summary, sharing a neutral between balanced and unbalanced 3-phase circuits can create a dangerous situation. It's essential to follow best practices and electrical codes to ensure the safety and reliability of your electrical system. Always consult with a qualified electrician if you have any doubts about your wiring configuration. Here are some additional points to consider. Firstly, always refer to the National Electrical Code, or NEC, for specific requirements regarding neutral conductors in 3-phase systems. The NEC provides detailed guidelines on conductor sizing, overcurrent protection, and grounding. Secondly, when designing a 3-phase system, it's essential to calculate the expected load on each phase and the potential for imbalance. This will help you determine the appropriate size for the neutral conductor. Thirdly, consider using separate conduits for the neutral conductors of balanced and unbalanced circuits. This can help prevent electromagnetic interference and improve the overall performance of the system. Fourthly, use appropriate overcurrent protection devices, such as circuit breakers or fuses, to protect the neutral conductors from overload. The overcurrent protection device should be sized to match the ampacity of the conductor. Fifthly, ensure that all neutral connections are properly made and tightened. Loose connections can create resistance, leading to heat buildup and potential failures. Sixthly, regularly inspect your electrical system for any signs of damage or wear. This includes checking for frayed wires, loose connections, and corroded terminals. Seventhly, if you are unsure about any aspect of your 3-phase system, consult with a qualified electrician. They can provide expert advice and ensure that your system is installed and maintained correctly. Here is a deeper dive into neutral sizing and NEC considerations. The NEC provides guidelines for sizing neutral conductors in 3-phase systems. The general rule is that the neutral conductor must be sized to carry the maximum unbalanced load. This means that you need to determine the largest possible difference in current between any 2 phases. In some cases, the NEC allows for a reduction in the neutral conductor size. This is permitted when the load is primarily nonlinear, such as lighting or electronic equipment. Nonlinear loads generate harmonic currents, which can increase the current in the neutral conductor. The NEC provides specific rules for calculating the neutral conductor size in these situations, outlined in NEC section 220.61. In dwelling units, NEC section 220.61 code provides guidance on sizing the neutral for ranges and cooking appliances. The neutral demand factor can be applied to the feeder neutral load calculation. For electric ranges, ovens, and cooktops, you can size the neutral based on 70% of the range's demand load. In commercial buildings with high harmonic content, the neutral conductor may need to be larger than the phase conductors. This is because harmonic currents can add up in the neutral conductor, potentially exceeding the capacity of the phase conductors. When dealing with circuits supplying electric vehicle charging equipment, you also need to consider the impact on the neutral load. Electric vehicle chargers can draw significant current, especially during peak charging times. Make sure your service and neutral conductors are sized to accommodate the additional load. Furthermore, it's vital to understand multi-wire branch circuits, or MWBCs. These circuits share a single neutral conductor between two or more hot conductors from different phases. MWBCs can save on wiring costs and reduce voltage drop, but they also require careful planning and execution. The NEC requires that the hot conductors of an MWBC be connected to different phases. This helps to balance the load and reduce the current in the neutral conductor. If the hot conductors are connected to the same phase, the neutral conductor can be overloaded. Additionally, NEC section 210.4b requires a device to simultaneously disconnect the ungrounded conductors of a multi-wire branch circuit at the point where the branch circuit originates. This protects against accidental energizing of the circuit during maintenance or repairs. When working with MWBCs, it is also important to use a common trip circuit breaker or handle tie to disconnect all the hot conductors simultaneously. This prevents a situation where one hot conductor is disconnected while the other remains energized, creating a shock hazard. Proper grounding is essential for the safe and reliable operation of any electrical system. The grounding system provides a low impedance path for fault currents, helping to trip over current protection devices and prevent electrical shock. The NEC provides detailed requirements for grounding electrical systems, including conductor sizing, grounding electrode systems, and equipment grounding. Make sure to follow these requirements carefully to ensure that your electrical system is properly grounded. Also remember that you cannot run multiple circuits through the same conduit without adhering to the requirements stated in NEC 300.3b. Always install the ungrounded and neutral conductors in the same raceway. Failure to do so could result in overheating of the conductors and conduit. When dealing with sensitive electronic equipment, it may be necessary to provide isolated grounding. Isolated grounding helps to minimize noise and interference in the grounding system, improving the performance of the equipment. The NEC provides specific requirements for isolated grounding in Article 250. Lastly, remember that electrical codes and standards are constantly evolving. Stay up to date on the latest changes to the NEC and other relevant codes to ensure that your electrical system is always in compliance. This requires ongoing training and education, as well as a commitment to safety and best practices. To further understand the intricacies of three-phase systems and neutral conductors, consider these scenarios. Imagine a small office building with a three-phase, 4-wire, 208Y/120 volts electrical service. The building has several branch circuits supplying power to lighting, receptacles, and HVAC equipment. One set of 3 branch circuits serves a row of cubicles, with each circuit connected to a different phase, A, B, and C. The lighting in each cubicle is balanced, drawing approximately 5 amps per phase. In this scenario, the neutral conductor for these 3 circuits will carry very little current, as the load is balanced across the 3 phases. However, another set of 3 branch circuits serves the small server room. 2 of these circuits are connected to phase A, while the third is connected to phase B. The servers on phase A draw 15 amps each, while the servers on phase B draw 10 amps. In this case, the neutral conductor for these three circuits will carry a significant amount of current as the load is unbalanced. To calculate the neutral current, you can use the following formula. Neutral current equals square root of IA2 plus IB2 plus IC2 IA asterisk IB IB asterisk IC IC asterisk IA, where IA, I, and IC are the currents in phases A, B, and C respectively. In this example, IA equals 30 amps, IB equals 10 amps, and IC equals 0 amps. Plugging these values into the formula, we get neutral current equals square root of 32 plus 10 2 plus 0 230 asterisk 10 10 asterisk 0 0 asterisk 30 equals square root of 900 plus 100 plus 0 300 0 0 equals square root of 700 equals 26.46 amps. This means that the neutral conductor for these three circuits will need to be sized to carry at least 26.46 amps. In addition to the unbalanced load, it is also important to consider the potential for harmonic currents in the server room. Servers and other electronic equipment can generate harmonic currents, which can increase the current in the neutral conductor. To account for harmonic currents, the NEC requires that the neutral conductor be sized to carry at least 125% of the calculated unbalanced load. In this example, the neutral conductor would need to be sized to carry at least 33.8 amps. 26.46 amps asterisk 1.25. To further illustrate the importance of proper neutral sizing, consider what could happen if the neutral conductor is undersized. If the neutral conductor is undersized, it can overheat and potentially cause a fire. Additionally, an undersized neutral conductor can cause voltage fluctuations on the circuits it serves, which can damage sensitive electronic equipment. In extreme cases, an undersized neutral conductor can even cause the equipment to malfunction. Therefore, it is crucial to follow the NEC guidelines for neutral sizing to ensure the safety and reliability of your electrical system. Also keep in mind the effects of voltage drop on your circuits. Voltage drop occurs when the voltage at the end of a circuit is lower than the voltage at the source. Excessive voltage drop can cause equipment to malfunction, overheat, or even fail. To minimize voltage drop, it is important to size conductors properly and keep circuit lengths as short as possible. The NEC provides guidelines for calculating voltage drop in Chapter 9. You can also use online voltage drop calculators to simplify the process. For example, a 120-volt circuit with a 3% voltage drop will have a voltage of 116.4 volts at the end of the circuit. This may be acceptable for some equipment, but it may not be sufficient for others. It's important to check the voltage requirements of the equipment you are using and ensure that the voltage at the end of the circuit is within the acceptable range. Moreover, regularly inspect your electrical system to identify potential problems before they become major issues. Look for signs of damaged or worn wiring, loose connections, and corroded components. If you find any problems, address them promptly to prevent further damage or safety hazards. Keep in mind that electrical work can be dangerous. If you are not comfortable working with electricity, hire a qualified electrician to do the job. Always follow safety precautions when working with electricity, such as wearing appropriate personal protective equipment, de-energizing circuits before working on them, and using insulated tools. Electricity can kill, so it is always better to be safe than sorry. In conclusion, understanding the principles of three-phase power systems, neutral conductors, and electrical codes is essential for anyone working with electricity. By following best practices and adhering to the NEC, you can ensure the safety and reliability of your electrical system. Remember to consult with a qualified electrician if you have any questions or concerns.